Picture an ocean at night. There is no coastline, no lighthouse, no familiar mountain breaking the horizon. Only a wooden ship moving through darkness, lifted and lowered by a surface that never becomes still. Somewhere beyond that darkness there may be open water, or there may be an island, a reef, or a wall of rock. The people aboard can estimate how far north or south they have traveled. They can watch the sky. They can record the direction of the wind, the heading of the ship, and their best estimate of its speed. But there is one question they cannot answer with confidence. How far east or west are we? For much of the history of ocean travel, that uncertainty accompanied every long voyage. It did not mean that earlier mariners were helpless. Far from it. Sailors developed sophisticated bodies of knowledge from stars, winds, currents, birds, swells, coastlines, and accumulated experience. Polynesian navigators crossed immense distances through the Pacific long before Europeans arrived with precision watches. Indian Ocean pilots understood monsoon systems. Coastal communities everywhere learned the particular language of their own waters. But aboard the expanding fleets of early modern Europe, which increasingly relied on gridded charts and numerical positions, east and west remained stubbornly difficult to measure on the open sea. The missing coordinate was longitude. It sounds like an abstract problem, a matter for maps, mathematics, and old instruments displayed behind museum glass. In practice, it could decide whether a ship found a safe harbor or passed it unseen. Whether a voyage took weeks longer than expected. Whether food and fresh water lasted. Whether a fleet arrived together or scattered across hundreds of miles. Longitude affected trade, warfare, exploration, and empire. It affected the lives of sailors and passengers, and the societies encountered by ships whose range and confidence were steadily increasing. The most famous answer to this problem is a clock. More precisely, it is a sequence of remarkable timekeepers made by an English carpenter and self-taught clockmaker named John Harrison. The last of the famous sequence, known today as H4, looked less like the grand mechanical machine that many expected and more like an unusually large pocket watch. It proved that a timekeeper could preserve a reference time across an ocean with enough accuracy to reveal a ship's longitude. That achievement was real, it was extraordinary. And by itself, it was not quite the whole solution. Because the ocean was not solved in a single workshop, on a single voyage, or by a single man. It was solved through clocks and stars, artisans and astronomers, printed tables and better charts, government rewards and bitter arguments, repeated trials, and the slow education of trust. This is the story of the clock that solved the ocean, and of everything the clock still needed around it before the solution could travel the world. To understand why a clock could reveal a position, we first need to make the Earth turn beneath us. Imagine the planet as a sphere wrapped in a grid. The horizontal lines are lines of latitude. They tell us how far north or south we are from the equator. The equator is 0 degrees. The poles are 90 degrees north and south. Lines of latitude remain parallel. 1 degree of latitude corresponds to 60 nautical miles. And with the right observation, latitude can be read from the sky. In the northern hemisphere, the height of Polaris above the horizon gives a useful guide. More generally, navigators can measure the altitude of the sun or a known star and compare the observation with astronomical information for the date. This was not effortless. Clouds could hide the sky. The horizon could be difficult to see. A rolling deck could disturb the instrument. Calculations and reference tables could introduce errors. But compared with longitude, latitude offered something wonderfully direct. The sky changed predictably as a ship traveled north or south. Longitude is different. Its lines run from pole to pole. They tell us how far east or west we are from an agreed starting line, called a prime meridian. Today, that starting line is associated with Greenwich in London. But nature does not mark Greenwich as special. The equator follows from the geometry of a rotating Earth. A prime meridian is a convention. Before international agreement, different maps used different starting lines, often running through the nation or city that produced the chart. The geometry of longitude is simple. Measuring it from a moving ship is not. The key is time. The Earth turns once in roughly 24 hours. A full turn is 360 degrees. Divide 360 by 24, and the planet rotates through 15 degrees in 1 hour. That also means 1 degree in 4 minutes. As the Earth turns, noon arrives at different places at different moments. Local noon is the point at which the sun reaches its highest position in the sky for that location. If it is noon where you are, but a clock preserving the time at your chosen reference meridian says it is 2 in the afternoon there, your local noon has arrived 2 hours later. 2 hours multiplied by 15 degrees means a difference of 30 degrees in longitude. If reference time is ahead of local time, you are west of the reference meridian. If your local time is ahead, you are east. The ocean's invisible coordinate can therefore be translated into a difference between two clocks. One clock is the sun above the ship. The other must somehow remain connected to a distant meridian, even after the ship has sailed away. This is the part that sounds easy from the age of quartz watches and phones. Set a clock in London, carry it aboard, compare its time with local solar time, calculate the difference. But a useful clock could not merely be accurate on the morning a ship departed. It had to retain a stable rate for weeks or months. An error of 4 minutes meant an error of 1 degree of longitude. Near the equator, that is about 60 nautical miles. A daily error that seemed tiny on land could accumulate into a dangerous uncertainty at sea. And the sea attacked clocks in almost every way a clock disliked. It rolled and pitched. It shook the mechanism. It moved through heat and cold, damp and salt. Metal parts expanded and contracted. Oils thickened, thinned, or deteriorated. Friction changed. Springs delivered varying force as they unwound. Gravity acted differently on moving components as the ship changed orientation. The ordinary precision clock of the period relied on a pendulum. A pendulum wants a stable relationship with gravity and a firm, motionless floor. A ship provides neither. So the longitude timekeeper could not simply be a good land clock placed inside a strong box. It had to be a new kind of machine. Before anyone built that machine, navigators continued to work with an older and more flexible method. They kept an account of the ship's movement as carefully as they could. It was called dead reckoning. Dead reckoning begins with a known or estimated position. From there, the navigator records the ship's course, its speed, and the time spent traveling. Distance is speed multiplied by time. Draw that movement on a chart, and it produces a new estimated position. Direction came from the compass. Speed could be estimated with a log line, in which a line was allowed to run out behind the ship for a measured interval. The divisions on that line helped give us the nautical use of the word knots. The method is elegant. It is also an accumulation of everything the navigator does not know perfectly. A compass heading is not always the ship's true direction of travel. Wind can push a vessel sideways. Currents can carry it invisibly. Waves and steering corrections create a path more complicated than the neat line drawn on a chart. Speed changes, measurements are rounded. Human beings make transcription and arithmetic errors. Each estimate becomes the starting point for the next estimate. Imagine walking across a dark field by counting your steps. If your first direction is wrong by only a little, the error grows with distance. Now imagine that the ground itself is sliding beneath you in a direction you cannot see. That was the navigator's moving ocean. Celestial observations could correct part of the account. A reliable latitude gave the ship a horizontal line on the chart. The east-west position along that line remained uncertain. One practical strategy was to sail toward the latitude of the destination first, then travel east or west along it. This was sometimes called running down the latitude. It reduced one uncertainty, but not all of them. A ship might know it was on the same latitude as an island, and still not know whether that island was 50 miles ahead or had already passed unseen astern. Near a coast, the consequences became sharper. Open water tolerates a positional error. Rocks do not. Navigators sometimes built caution into their reckoning, arranging the estimate so they expected land before the ship was likely to reach it. Lookouts could then be posted early. Soundings could test the depth. Speed could be reduced at night. This was intelligent risk management, not primitive guesswork. But it cost time, and it depended on the quality of charts and local knowledge. That last point matters. Even a perfectly measured longitude is useful only if the dangers and destinations on the chart have also been placed correctly. A ship can know its coordinates with precision and still be endangered by a badly mapped reef. The solution to navigation would therefore require more than a coordinate. It would require surveying, chart-making, instruments, training, and procedures. Still, a dependable longitude promised an enormous improvement. European states and trading companies understood that improvement in very practical terms. Safer voyages could preserve ships, cargoes, and train crews. More direct routes could shorten exposure to disease and shortages. Fleets could coordinate more effectively. Surveyors could place coastlines and islands into a shared numerical world. There was money in a reliable east-west position. There was military power in it too. And as European maritime empires expanded, there was a growing political desire to make distant oceans easier to cross, map, and control. By the beginning of the 18th century, longitude was not merely a puzzle for mathematicians. It was a problem governments were willing to buy. The search for longitude did not begin in Britain, and it did not begin with John Harrison. European powers had offered rewards and patronage for longitude methods long before the British legislation of 1714. Spain, the Dutch Republic, and France all had reasons to encourage solutions. Every maritime state faced the same rotating planet and the same unstable sea. In Britain, one disaster has come to symbolize the urgency of the problem. On the evening of the 22nd of October, 1707, ships under Admiral Sir Cloudesley Shovel approached the Isles of Scilly after returning from the Mediterranean. 5 ships struck rocks, 4 went down. More than 1,400 men, including Shovel, died. The loss was immense, and navigational errors were involved. In many retellings, the disaster produces an immediate public outcry. Parliament responds, and the Longitude Act follows 7 years later. The real connection is less tidy. Historians have not found evidence for the public campaign that this familiar version requires. The disaster demonstrated the terrible stakes of uncertain navigation, but the act seems to have emerged more directly from lobbying by mathematicians and projectors, including William Whiston. This correction does not make the story less dramatic, it makes it more revealing. The British state did not suddenly discover longitude after one night of catastrophe. It was persuaded that a long-recognized technical problem could be attacked through legislation, expertise, and money. The Longitude Act received royal assent in July 1714. It offered graded rewards according to accuracy. £10,000 for a method that could determine longitude within 1 degree. 15,000 for 2/3 of a degree. 20,000 for half a degree under the conditions of the specified ocean trial. At the equator, half a degree is about 30 nautical miles. The largest reward was an extraordinary sum. But calling it simply the Longitude Prize can create the wrong picture. It was not quite a modern contest with a fixed deadline, a row of finalists and one ceremonial check. The legislation created possibilities for partial payments, trials, and support for promising schemes. Over time, public money went to many contributors: astronomers, instrument makers, mathematicians, clockmakers, calculators, and explorers. Even the body now remembered as the Board of Longitude did not spring to life in 1714 as a busy permanent agency with an office and regular schedule. The Act named commissioners. Their first recorded meeting did not occur until 1737, when Harrison's first sea clock forced the question of what should happen next. Only in the 1760s, amid competing schemes and disputes over Harrison's later watch, did the board develop the more regular meetings, records, and administration we associate with an institution. This matters because the Longitude program had to invent more than a navigation technique. It also had to invent a way of judging invention. How many successful voyages were enough? Who should supervise a trial? What counted as an error in the watch, and what counted as an error in the reference observations? Must an inventor reveal every working detail? Should public money reward a brilliant one-off object, or only a design that other makers could reproduce? These questions would eventually dominate John Harrison's life. But in 1714, there was no reason to assume that the winning idea would be a timekeeper at all. Some of the most promising clocks were already hanging in the sky. Long before a mechanical clock could keep reference time across an ocean, astronomers searched for events that the entire world could observe. If a celestial event occurred according to a predictable schedule, then the sky itself could provide the time at a reference meridian. Observe the event locally, compare it with the predicted reference time, convert the difference into longitude. Galileo proposed one of the most ingenious versions in the early 17th century. Jupiter has moons that repeatedly pass into the planet's shadow. Their eclipses can be predicted. In principle, those events form the face of a great celestial clock visible from widely separated places. On land, the method became useful for mapping. At sea, it collided with the deck. Watching a tiny moon disappear beside a distant planet requires a telescope and a steady line of sight. A ship rolls, pitches, and yaws. Even locating Jupiter through a narrow instrument can be difficult. Timing a precise eclipse from that platform was not a routine answer for mariners. Inventors proposed chairs, supports, and other devices to stabilize observers. The schemes could be wonderfully elaborate. They never made Jupiter's moons a practical general solution at sea. The Earth has a closer moon, however, and our moon moves rapidly against the background stars. That movement suggested another kind of clock. At any given moment, the angular distance between the moon and selected stars is predictable if the moon's irregular orbit can be calculated accurately enough. A navigator measures that angle. Tables reveal the reference time at which the moon should have occupied that position. The navigator compares it with local time and obtains longitude. This is the lunar distance method, often shortened to lunars. Its difficulty was divided among several different technologies. First, astronomy had to predict the moon. That was a formidable mathematical problem. The gravitational influence of the sun complicates the moon's orbit around Earth. Even Newton's powerful theory did not, by itself, immediately produce predictions convenient and accurate enough for routine longitude at sea. Second, an instrument had to measure small angles from a moving ship. Earlier quadrants and related devices evolved toward the sextant, which uses mirrors to bring two objects into the observer's view at once. The navigator can align the moon's edge with a star or the sun, while the horizon and deck move below. Third, the observation had to be corrected. Refraction bends light through the atmosphere. The apparent edges and altitudes of celestial bodies differ from their ideal geometric positions. The navigator had to clear the measured lunar distance through calculation. And finally, someone had to turn theory into tables that a working navigator could carry. The Hanoverian astronomer Tobias may have made a critical advance in lunar tables, drawing on careful observations associated with James Bradley, the Astronomer Royal. The London instrument maker John Bird refined a brass angle measuring instrument through trials, contributing to the first marine sextant. Bradley concluded that Mayer's tables and a capable instrument could bring longitude within 1 degree. That placed the method inside the limits contemplated by the 1714 Act. In 1761, the young astronomer Neville Maskelyne tested lunar distances during a voyage to St. Helena. His lunar result at the end of the passage was about 1.5 degrees in error. The ship's dead reckoning had wandered by as much as 10 degrees. The method worked, but the calculations were slow. Maskelyne recognized that much of the burden could be moved ashore. After he became Astronomer Royal in 1765, he organized the Nautical Almanac and Astronomical Ephemeris. Human calculators prepared future positions and other data in advance. The information for the year 1767 was ready for printing by the end of 1766. The almanac was a machine made from paper and labor. It converted observatory data and repeated arithmetic into something a navigator could take to sea. It would become one of the two great practical answers to longitude. The other answer was already ticking in John Harrison's workshop. John Harrison did not arrive from the centre of London's scientific establishment. He was a carpenter by trade, raised in the north of England and largely self-taught as a clockmaker. This background has often made him a perfect hero for later stories, the practical provincial craftsman challenging educated astronomers and powerful institutions. There is truth in the contrast, but less isolation than the legend suggests. Harrison's work depended on relationships with other skilled people. His brother James probably helped construct H1. The astronomer Edmund Halley listened to his proposal and directed him toward George Graham, one of the most respected clockmakers in London. Graham gave support rather than dismissal. Later, specialist watchmakers would help turn Harrison's ideas into working precision watches. Harrison's ability was already evident in the precision long-case clocks he made during the 1720s. Royal Museums, Greenwich reports that these achieved an accuracy of about 1 second in a month, remarkable for the period. He reduced friction with carefully chosen materials and ingenious mechanical design. He worked with wood in places where another maker might have chosen metal. He developed mechanisms that could maintain a more stable rate as temperature changed. For longitude, Harrison aimed at a portable clock that would keep within about 3 seconds per day. That target required him to reconsider the heart of the clock. The pendulum had to go. His first marine timekeeper, now called H1, used two interconnected balances moving in opposition. Where the motion of a ship might disturb one, the paired arrangement was intended to cancel the effect. Springs controlled their movement. The machine carried ideas from Harrison's precision wooden clocks into a form that did not need a stable wall or floor. H1 did not look like a pocket watch. It was a gleaming framework of brass, steel, and wood, more than 1/2 meter across, visibly alive with linked motion. Harrison worked on it in Barrow upon Humber and brought it to London in 1735. It was placed in George Graham's workshop and shown to members of the scientific community. The following year, Harrison and H1 sailed for Lisbon aboard His Majesty's ship Centurion. The outward passage was not a smooth triumph. Harrison became ill, and the machine's performance was less reliable early in the voyage. After reaching Lisbon, H1 returned aboard His Majesty's ship Orford and behaved more convincingly. As the ship approached England, the officers believed a headland ahead was Start Point. Harrison used his timekeeper and observations to argue that it was actually the Lizard, much farther west. He was right. The ship's own reckoning was off by roughly 60 miles. This was not the full transatlantic test described by the Act, and H1 was not ready to become a standard shipboard instrument. But the moment supplied something extremely valuable, a practical demonstration in waters where the officers could recognize the correction. Harrison had not merely built an interesting clock. His machine had contradicted a ship's navigation and been vindicated by the land itself. In June 1737, 8 commissioners met to consider what one record called Harrison's curious instrument. It was the first recorded meeting of the Longitude Commissioners, named under the 1714 legislation. They awarded him £500. Half would be paid in advance so that he could build an improved timekeeper. At this stage, the relationship was supportive. Harrison had money, recognition, and a clear invitation to continue. He promised an improved clock in 2 years. The next stage would occupy him for more than 20. Harrison completed his second sea clock, H2, within roughly the promised time. It was larger and heavier than H1, with a more powerful and carefully arranged mechanism. It was intended to correct weaknesses discovered in the first design. But H2 never received its trial at sea. This is sometimes compressed into the statement that H2 failed. The more interesting truth is that Harrison himself identified a fundamental problem before submitting it. The paired bar balances could be disturbed by certain turning motions of a ship. A design that resisted rolling and pitching was still vulnerable when the vessel changed direction around its vertical axis. Harrison had reached one of engineering's most difficult moments. The machine in front of him represented years of intricate work. It was more advanced than his celebrated first attempt. Public money and reputation were attached to it, and its underlying arrangement could not deliver the result he wanted. He did not send it to sea and hope the flaw remained hidden. He moved on. In 1740, he began H3. He would continue working on it for around 19 years. H3 replaced the long bar balances with two large circular balances. These were linked and controlled by springs, seeking the stable rhythm that a pendulum could not provide aboard ship. The basic challenge of a clock is not simply to make parts move. It is to make an oscillator repeat the same interval under changing conditions. If a balance swings slightly farther on one beat than another, does it take the same amount of time? If the spring becomes more elastic in warmth, does the rate change? If friction rises as the mechanism turns, does the clock slow? If the main power spring delivers less force near the end of its winding, does the balance receive a weaker impulse? At sea, these questions combine. Temperature changes the dimensions and properties of materials. A steel spring in tropical heat does not behave exactly as it did in an English workshop. Lubrication can become a source of changing resistance. Bearings wear. A moving ship adds accelerations that the mechanism must somehow ignore. Harrison attacked each effect through physical design. H3 did not become the Longitude winner, but it produced inventions that traveled far beyond marine timekeeping. One was the bimetallic strip. Join two metals that expand at different rates, and a change in temperature causes the strip to bend. That movement can be arranged to compensate for a temperature-driven change elsewhere in the machine. The same simple principle later appeared in countless thermostats. Another was the caged roller bearing. By keeping small rollers separated and controlled, the bearing reduced sliding friction and allowed smoother motion. Variations of the idea became common throughout mechanical engineering. These inventions are a reminder that a prototype can fail at its declared purpose and still transform the future. H3's balances never kept a sufficiently stable rate. Harrison adjusted, rebuilt, and reconsidered. Years passed. The problem seemed to be expanding rather than narrowing. Then the direction of the entire project changed. Harrison had been exploring precision watches alongside the great sea clocks. Around 1751 or 1752, he commissioned the watchmaker John Jeffreys to build a watch to Harrison's design, including a radically different balance. The result performed far better than conventional assumptions about watches suggested. In the middle of his struggle with a large machine, Harrison encountered the possibility that the solution might be small. This was not an obvious conclusion. An 18th century watch was portable, but portability did not mean precision. Watches were affected by position, temperature, friction, and variable power. Their small components demanded exceptional workmanship. A watch might be convenient for telling a gentleman approximately what hour it was. It was not the natural instrument on which to risk a ship's position after weeks at sea. Harrison began to think otherwise. He did not merely shrink H3, he changed the architecture of the answer. The clock that solved the ocean was about to become a watch. Work on H4 began in 1755 and was completed in 1759. Place it beside H1, H2, and H3, and it seems to belong to another family. The earlier machines display their structures openly. H4 sits inside a silver case. Its dial is about 10 centimeters across. It weighs roughly 1.5 kilograms. Large for a pocket, certainly, but astonishingly compact beside the machines that preceded it. Its appearance can be misleading. H4 was not an ordinary watch made slightly better. It was a dense concentration of Harrison's long attempt to control motion, power, temperature, and friction. The first clue is its sound. H4 ticks 5 times each second. Its balance moves faster and through larger oscillations than the balance in a typical watch of the period. A high-frequency oscillator can be less affected, proportionally, by small disturbances. Each individual error has less opportunity to dominate the rate. The balance spring was carefully shaped. Temperature compensation adjusted the regulating system as heat altered the spring. Jeweled surfaces reduced friction in critical places. Diamond pallets met the escape wheel. A remontoire helped isolate the regulating mechanism from changes in the force supplied by the mainspring. That word, remontoire, describes a small secondary store of energy inside the movement. The main spring does not push the escapement with all its changing force directly. Instead, it periodically rewinds the smaller mechanism, which delivers a more consistent impulse. Think of pouring water from a large, unevenly flowing container into a small cup that is repeatedly refilled. The cup helps deliver a more regular amount, even as conditions in the larger container change. Every element demanded extraordinary workmanship. Brass, steel, silver, diamond, ruby, enamel, copper, and glass were brought together in an object that had to remain consistent while the world moved around it. H4 also carried a lesson Harrison had spent decades learning. A sea timekeeper did not have to fight the ship by becoming heavier and more monumental. It could resist disturbance through a faster, carefully controlled internal rhythm. This is why H4 is more than the fourth item in a neat series. The sequence from H1 to H4 is not a straight path of gradual miniaturization. It includes abandoned principles, long detours, and a late change of scale. H1 proved that a non-pendulum marine clock could be plausible. H2 revealed a hidden sensitivity in the balance system. H3 failed to reach the required rate, but generated important methods for temperature and friction. The Jeffreys watch showed that a small, fast balance could become a precision instrument. H4 gathered the surviving ideas into a different form. There is a temptation, when looking backward, to treat every earlier machine as if it was destined to lead here. Harrison could not see the sequence from above. He spent years inside each uncertainty. By 1759, he was 66 years old. He had a watch that appeared capable of meeting the greatest public reward of his age. But workshops do not award navigation claims. Oceans and institutions do. H4 now had to travel. In 1761, the commissioners authorized a trial voyage to Jamaica. John Harrison did not carry H4 himself. His son William took responsibility for the watch aboard His Majesty's ship dipped forward. The procedure began before departure. The timekeeper's rate had to be observed against reference time. It was then sealed and protected. During the voyage, William maintained it and used it to calculate longitude. Early in the passage, H4 produced a memorable practical prediction. The ship's officers expected Madeira to appear later. William Harrison, trusting the watch, calculated that landfall would come sooner. His prediction proved correct. The captain was sufficiently impressed to express interest in buying a future timekeeper. At Jamaica, observations provided the comparison needed to judge how well H4 had carried reference time across the Atlantic. The reported result was remarkable and comfortably suggested that the watch could satisfy the highest accuracy threshold contemplated by the original act. For the Harrisons, the meaning seemed plain. The method had crossed the ocean. The watch had worked. The reward was due. The commissioners did not agree that the matter was finished. One voyage could be unusually favorable. The watch's behavior might have been helped by handling known only to William. The destination's reference longitude and the observations used to judge the result introduced their own uncertainties. A method intended for public navigation needed more than a single impressive performance. The board's caution was not inherently unreasonable, neither was Harrison's anger. He had spent decades responding to requests for improvement. The original legislation had described an ocean trial and an accuracy. H4 appeared to have passed. From his perspective, new demands arrived only after success. This is where the warm relationship of earlier years began to harden. Harrison's supporters took the case into print. Pamphlets and newspaper arguments turned technical procedure into public controversy. The question was no longer only whether H4 kept time. It was whether the institutions judging it were fair. Meanwhile, other longitude methods were ready for comparison. Tobias Mayer's lunar tables had become credible. Instruments had improved. A scheme for observing Jupiter's satellites from a ship still had advocates. A more elaborate trial was organized around Barbados in 1763 and 1764. Neville Maskelyne traveled as the astronomer responsible for establishing the island's longitude through observations. William Harrison followed with H4. Lunar distances, Jupiter's moons, and the Sea Watch would all be tested within the same broader program. When the board considered the results in February 1765, it confirmed that H4 had kept time within the most stringent limit of the 1714 Act. That sentence sounds like the end. Instead, it opened the deepest dispute in the story. The board recommended that Harrison receive £10,000 after revealing the principles of H4. The remaining amount, less earlier payments, would follow when it had been shown that other makers could produce similar timekeepers. Parliament formalized the new conditions in May 1765. The commissioners wanted a public solution, not a secret object. They wanted to know whether H4 was a repeatable technology or the unique product of one aging master and his son. The Harrisons believed the rules had been changed after they had already met them. Both positions reached beyond the watch. What exactly had the state promised to buy? Suppose a government offers an enormous reward for a method that can determine longitude at sea. An inventor produces one extraordinary machine. Under the inventor's care, it passes the required voyage. Has the problem been solved? For the inventor, the answer may be yes. The machine proves the method. The stated performance has been achieved. Years of private skill and sacrifice deserve the promised reward. For the government, the answer may be incomplete. Can a different maker reproduce the machine? Can naval officers use it without the inventor present? Can it be repaired? How much will it cost? Does it work across heat, cold, and multiple voyages? What knowledge must become public in exchange for public money? These were not abstract questions in the Harrison dispute. H4's success forced the Longitude program to define what success meant. Harrison was required to explain the principles and construction of his watch. A panel of experts examined it. The clockmaker Larkham Kendall received a commission to make a copy. For Harrison, disclosure threatened control over the product of a lifetime. His knowledge was not only a list of parts. It lived in proportions, finishing, adjustment, and judgment. Explaining a mechanism did not instantly transfer the maker's hands. For the board, a solution locked inside those hands could not yet serve the nation in the way the reward intended. The conflict has often been retold with Neville Maskelyne as Harrison's personal enemy. Maskelyne makes a convenient villain. He was an astronomer advocating lunar distances. He became Astronomer Royal. He participated in the trials and later tested H4 at Greenwich. In a simple contest between clocks and stars, his professional interest appears obvious. But the evidence does not support a melodrama in which Maskelyne secretly prevents a superior technology from winning. Astronomy and timekeeping were not mutually exclusive camps. A chronometer still required astronomical observations to establish local time and to check its rate. A lunar observation could test or correct a watch. Maskelyne's nautical almanac served navigation broadly, including calculations used alongside timekeepers. The board itself was becoming a more regular institution, partly because Harrison's case demanded procedures, records, and defensible decisions. Its commissioners worried about trials, standards, and public accountability. Harrison and his supporters worried that bureaucracy was being used to deny a clear achievement. The distrust was mutual, and it was intensified by publication on both sides. In May 1766, Maskelyne received H4 for a long trial at the Royal Observatory in Greenwich. The watch arrived, locked in a box under seals. Over the following 10 months, it did not perform as well as it had on the ocean voyages. Maskelyne published the results. Harrison challenged the way the trial had been conducted and interpreted. A stationary observatory test might sound easier than a voyage. Yet watches can change rate with orientation, handling, and temperature. Decisions about winding, comparison, averaging, and correction matter. A test is never simply nature speaking without human procedure. The poor Greenwich performance did not erase H4's sea trials. Neither could the sea trials answer every concern about reproduction and general use. The dispute moved toward politics. William Harrison approached King George III. Harrison built another watch, H5, and it was observed at the King's private observatory at Kew. The king became sympathetic to the family's case. John Harrison petitioned Parliament. In 1773, Parliament granted him a further payment for his service to the nation. By then he had received substantial sums across the decades, though not through the simple, satisfying scene of the board handing him an undivided £20,000 prize. He was 80 years old. 3 years later, he died. Was Harrison treated unfairly? There are strong reasons to understand his frustration. H4 met the strictest performance limit, and additional conditions were formalized afterward. The process consumed precious years near the end of his life. There are also strong reasons why a publicly funded navigation system required disclosure, independent construction, and repeated tests. The most honest conclusion is not that the conflict had no villains or no injustice. It is that the dispute joined two legitimate meanings of invention that did not align. Harrison had demonstrated a masterpiece. The board wanted infrastructure. Between those two things stood replication. While Harrison fought to secure recognition for H4, the astronomical solution was becoming a practical service. To take a lunar distance, a navigator used a sextant to measure the angle between the moon and the sun, or a selected star. The observation had to be taken carefully, often several times. Additional altitudes were measured. Corrections removed the effects of refraction and the observer's position on Earth. The cleared distance was compared with the nautical almanac. The result revealed the reference time associated with the moon's position. Local time completed the longitude calculation. This demanded skill. The observer had to identify stars, handle a fine instrument on deck, and perform or supervise substantial arithmetic. It also offered one advantage that no mechanical watch could guarantee. The sky did not need winding. A timekeeper could stop. It could be damaged. It could change rate without obvious warning. If a ship carried only one, the navigator needed a way to judge whether its time remained trustworthy. Lunars provided an independent route back to reference time whenever the sky and the observer's skill allowed. The nautical almanac made this route much shorter by transferring computation from the ship to a network on land. At the center of that network were observations from places such as Greenwich. Around them were mathematicians, editors, printers, and human computers. The word computer described a person before it described a machine. These workers converted astronomical theories and observations into rows of predicted positions. The labor could be tedious and poorly paid. It was also essential. A navigator opening a table in the South Atlantic depended on calculations performed months or years earlier by people who would never see the voyage. Among them was Mary Edwards, one of the few women known to have contributed extensively to the nautical almanac in this period. She performed calculations and later helped train other computers, including her daughters. Her place in the story widens the workshop. The longitude solution was made not only by celebrated inventors, whose names were engraved on brass. It was also made by people copying figures, checking arithmetic, comparing observations, and preparing pages whose greatest achievement was to seem routine. That routine was Maskelyne's great contribution. He did not defeat Harrison, nor did Harrison make Maskelyne irrelevant. The lunar distance method and the marine timekeeper answered different weaknesses in one another. Lunars required clear skies, a skilled observer, and lengthy work. A timekeeper could offer longitude quickly, even when the moon was unavailable, but it was costly and could drift or fail. A prudent navigator had reason to value both. This is why the story cannot end with H4's first successful voyage. The real solution was becoming a practice in which several imperfect methods watched over one another. On a well-run voyage, the navigator did not choose one method and throw the others overboard. Dead reckoning continued hour by hour. It was immediate, familiar, and always available. Course, speed, wind, and estimated movement were entered into the ship's account. When the sky allowed, observations supplied a fix. Latitude corrected the north-south position. A timekeeper offered longitude by comparison with local solar time. A lunar distance could independently recover reference time and check the watch. Near land, soundings, bearings, and local knowledge mattered. Under all of it lay the chart, which might be excellent, incomplete, or dangerously wrong. The methods were layered because uncertainty was layered. If the dead reckoning and the watch disagreed, the navigator could investigate. If two timekeepers disagreed, neither announced which one was faulty. If the moon confirmed one, confidence increased. If clouds prevented observations for days, the running account remained. Redundancy did not show that the new technology had failed. It showed that seafarers understood the ocean too well to trust a single source of information without question. The board of longitude gradually supported this wider system. It sponsored trials, publications, and instruments. It helped organize astronomical observation and expeditions. Its archive contains not one triumphant solution, but thousands of pages of proposals, reports, calculations, correspondence, and judgment. Some schemes were brilliant, some were impractical. Some now appear eccentric. Together, they show a culture learning how to convert private ideas into public knowledge. That conversion included teaching. A sextant is only useful in trained hands. A table is only useful to someone who understands its entries. A watch needs winding, protection, and a known rate. A chart needs symbols and conventions shared by its users. The celebrated instrument is often the most visible part of a technology because it can be placed in a glass case. The less visible parts are procedures. Consider local time. H4 carried reference time, but the navigator still needed the time at the ship. Observing the sun near noon seems simple until precision is required. The sun's apparent motion is slowest near its highest point, making the exact instant of noon hard to judge directly. Navigators developed observations and calculations suited to the available conditions. Isaac Newton had recognized a version of this limitation before Harrison's clocks. A clock alone does not announce a complete longitude. It becomes part of a method joining mechanical time with astronomical observation. This is the point at which the phrase, solved longitude, becomes both true and misleading. Harrison solved the central mechanical problem. He demonstrated that reference time could survive a long voyage with extraordinary accuracy. Mayer, Maskelyne, Bird, and many others helped solve the astronomical and computational problem. Surveyors solved the problem of placing coastlines, harbors, and hazards onto better charts. Makers after Harrison solved the problem of building useful timekeepers in greater numbers. Navigators solved the practical problem anew on every voyage. The decisive demonstration of that combined practice would take place far beyond the Atlantic trials, across some of the largest and least familiar waters on European maps. For that voyage, the board sent a copy of H4 rather than H4 itself. Its name was K1. Larkham Kendall was one of the skilled London watchmakers asked to turn Harrison's disclosed principles into another instrument. The board commissioned him in 1766 to copy H4 part for part. Kendall completed the work in 1769. When the copy was examined the following year, even William Harrison acknowledged the quality of its construction. The watch is now known as K1. Replication was a success, but it revealed the next problem. Kendall received £450 for the watch, plus an additional 50 for the extraordinary work involved in adjusting it and taking the mechanisms apart. The design could be copied by a first-rate maker. It could not yet be produced cheaply or quickly. K1 was nevertheless ready for a far greater test. In 1772, James Cook departed on his second Pacific voyage aboard His Majesty's ship Resolution. One purpose of the expedition was to search the high southern latitudes for the hypothetical great continent some Europeans expected to find. It was also a moving laboratory for navigation. K1 traveled with the expedition, alongside other timekeepers, sextants, and the nautical almanac. The astronomer William Wales carried out extensive observations. Across 3 years, changing climates and immense distances, K1 performed remarkably well. Cook came to call it his trusty friend and his never-failing guide. Those affectionate fragments are powerful because they describe trust earned in use. H4 had passed controlled Atlantic trials. K1 showed that the design could support navigation through a long, complex expedition far from the maker's workshop. Cook did not simply read longitude from the watch like a modern coordinate display. The navigators maintained dead reckoning over shorter intervals. They used astronomical observations with the timekeeper. They took lunar distances to obtain an independent reference and assess the watches. They compared instruments and results. K1 became central because it made an accurate longitude available with far less work between those checks. It carried a stable temporal bridge back to Greenwich, while resolution crossed seas on the other side of the world. The resulting charts were extraordinarily important to European navigation. They also belonged to voyages of imperial expansion. Cook's crews entered worlds that were not empty and waters that were not unknown to the people who lived there. Pacific navigators possessed traditions capable of linking islands across vast distances through stars, waves, winds, wildlife, and memory. European longitude instruments did not create navigation in the Pacific. They enabled European states to map those waters into their own coordinate systems with increasing precision. That precision served science and safer passage. It also supported claims, trade, military reach, and later colonization. The clock's legacy, therefore, cannot be separated neatly into innocent discovery on one side and politics on the other. A more capable navigation system changes who can travel, return, map, and exert power. K1 itself continued through an extraordinary career. It accompanied Cook again, later traveled with the First Fleet to Australia, and served on other naval voyages before returning to the board. But the future of marine timekeeping could not depend on instruments built at K1's cost. The masterpiece had been replicated. It still needed to become a product. Harrison's most famous watches proved what precision timekeeping could do. Their complexity ensured that later makers would not simply reproduce them forever. Kendall himself attempted cheaper versions. K2 cost £200, K3 cost £100. Both simplified H4, and neither matched K1's performance. This was another valuable result. It showed that complexity could not be removed indiscriminately. Some features that looked expensive or fussy were doing essential work. Other makers found different routes. John Arnold developed precision watches and marine timekeepers with designs better suited to manufacture. He helped establish the term chronometer for an exceptionally accurate timekeeper. Thomas Earnshaw further simplified the marine chronometer around a form that could be reproduced and maintained more economically. There were disputes over priority, patents, and rewards, just as there had been around Harrison. The commercial chronometer was not the unaltered child of one machine. It emerged from a skilled trade, experimenting with balances, springs, escapements, compensation, and methods of production. By the early 19th century, chronometers were becoming more widely available. They remained valuable instruments. Ships might carry several, so their rates could be compared. Naval observatories and specialist makers rated, serviced, and repaired them. This support network was part of the technology. Before a voyage, a chronometer's gain or loss per day could be measured against a trusted reference. That known rate allowed the navigator to correct its reading. A good instrument did not need to show perfect time every instant. It needed to change predictably. The distinction is subtle and important. Accuracy is closeness to the correct time. Stability is consistency of rate. A stable chronometer that gains a known amount each day can be extremely useful. An instrument that is correct this morning, but changes its rate unpredictably, is dangerous. Harrison's long battle had always been a battle for stable rhythm. As chronometers became practical, lunars did not disappear overnight. Astronomical methods remained valuable checks, particularly when instruments were scarce or a timekeeper's reliability was uncertain. Dead reckoning remained fundamental. Charts continued to improve. The transformation happened gradually, voyage by voyage, port by port. This slow adoption is easy to overlook because museums preserve exceptional beginnings. H4 sits at the center of the story because it is beautiful, personal, and revolutionary. Routine chronometers in wooden boxes can appear less dramatic. Yet routine was the real victory. A solution becomes world-changing when people who never met the inventor can use it, teach it, repair it, and trust it without treating every operation as an experiment. By that measure, the longitude problem was not solved on one date. Not in 1759, when H4 was completed, or in 1761, when it crossed to Jamaica. Not in 1765, when the board confirmed its performance, or in 1773, when Parliament compensated Harrison. It was solved across a long transition, in which precision time became an ordinary working instrument of the sea. The final step was to agree more broadly on what time those instruments should carry. Longitude can be measured from any chosen reference meridian, provided the navigator's time and charts use the same one. For centuries, maps began from different places. Greenwich, Paris, and other meridians coexisted. This was workable within a shared system and confusing between systems. The Royal Observatory at Greenwich had been founded in 1675 partly to improve the astronomical knowledge needed for navigation. Its observations supported tables, almanacs, and the rating of timekeepers. As British charts and maritime influence spread, Greenwich became an increasingly common reference. In 1884, an international conference selected the Greenwich meridian as the international prime meridian. The decision did not make Greenwich natural. It made one convention dominant. By then, precise time had escaped the ship's box. Railways and telegraph networks made differences in local solar time inconvenient on land. Towns that had once kept their own noon increasingly synchronized. Observatory time, signals traveled through wires. Later they traveled by radio, allowing ships to check chronometers without waiting for a lunar observation or returning to port. The reference clock was no longer only an object carried from home. Reference time could be transmitted. During the 20th century, the definition and production of time moved from astronomy toward atomic physics. The second was eventually defined using a transition in cesium atoms rather than a fraction of the variable solar day. The machines changed beyond anything Harrison would have recognized. The navigation principle remained strangely familiar. The global positioning system uses satellites carrying atomic clocks. The satellites broadcast their position and precise time. A receiver compares when signals were sent with when they arrived. Because radio waves travel at the speed of light, a tiny difference in time corresponds to a measurable distance. With signals from several satellites, the receiver solves for position and for the error in its own clock. H4 compared local solar time with a reference time carried across the Atlantic. GPS compares the travel times of radio signals from moving clocks in orbit. The mathematics and machinery are profoundly different. But both systems reveal the same deep relationship. Position can be extracted from time. The precision has changed, almost beyond intuition. Harrison fought for seconds per day. Satellite navigation depends on billionths of a second and corrections that include the effects of relativity. And yet modern navigation still depends on infrastructure around the clocks, monitoring stations, orbital models, transmitters, receivers, maps, software, and agreed standards. There is still no magical object that solves location alone. There is a system that makes astonishing complexity feel immediate. Tap a destination on a phone, and a blue point appears. It seems to know where it is without effort. Inside that ordinary moment is the descendant of a much older idea. Keep or receive a trustworthy time, compare it with another event, and turn the difference into distance. The title of this story contains a small exaggeration. No clock solved the ocean. The ocean did not become still. Currents did not stop moving ships. Clouds did not leave the sky. Reefs did not place themselves correctly on charts. Human error did not disappear. What Harrison's clock solved was an invisible relationship. It connected a ship to a distant meridian through time. Before departure, the watch learned the rhythm of home. At sea, it carried that rhythm through motion, temperature, and weeks of separation. When the sun revealed local time, the difference between the two became an east-west position. Harrison's achievement was to build a mechanical memory of place. H1 showed that such a memory could survive a ship. H2 revealed a flaw before the sea did. H3 consumed 19 years and left behind inventions that reached into other machines. H4 transformed the problem into the rapid heartbeat of a watch. Then the story widened. Commissioners argued over evidence. Watchmakers attempted copies. Astronomers refined the moon's motion. Instrument makers improved the sextant. Human computers filled almanacs with future skies. Surveyors redrew coastlines. Navigators compared every method they could use. K1 crossed the Pacific and became a trusty friend, not because it replaced judgment, but because it earned a place inside it. Arnold, Earnshaw, and other makers changed a masterpiece into a family of reproducible instruments. Observatories supplied reference time. International agreement supplied a common meridian. Radio and atomic physics eventually replaced the carried clock with transmitted time. The longitude problem was solved when all of these pieces became ordinary enough to be trusted. That may be the quieter lesson of the story. We remember invention as a flash. One person, one object, one successful test. But the technologies that change the world usually pass through a longer transformation. They must move from insight to evidence, from evidence to argument, from argument to replication, and from replication to routine. Harrison gave longitude its most charismatic object. The wider world made that object into a system. Tonight, ships cross the same oceans under the same moving sky. Their crews can know their positions with a precision no 18th century navigator would have believed. Signals fall silently from atomic clocks in orbit. Charts update on glowing screens. Reference time surrounds the planet. And beneath all of it remains a simple fact about a turning Earth. 15 degrees in an hour. 1 degree in 4 minutes. Keep the time of a distant place, and the ocean begins to reveal where you are.